Welcome back. In the last part, we are discussing about the spectrum, absorption spectra, emission spectra, and also we have discussed the line spectrum, band spectrum, and the continuous spectrum. So that part I think cleared. So now we will discuss the result obtained during the experiment of the hydrogen atom in taking in the discharge tube. That means the atomic spectra of the hydrogen atom or the hydrogen spectrum. So what was the result? So if you look at the visible range first, what was the result? In visible range, there were 4 lines. Okay, so let me make the heading. What that is the Balmer series of hydrogen atom, not atom spectra. Okay, so this is the Balmer series of hydrogen spectrum. What I have said, in the visible range, let's focus the atomic the visible range of the atomic spectrum, visible range of the hydrogen spectrum more specifically. So there are 4 lines obtained in the result. So these experiments were, I am repeating again, these experiments were done in late 19th century. That means 1880 or that around. So before the Bohr's atomic model. Bohr's atomic model was given in 1910 after Planck's hypothesis in 1901, then the Einstein photoelectric effect 1905. After that, but these experimental results were very known, but that was not explainable at that time. Okay, so let's say what was the line? What was the result? In visible range, there are 4 lines obtained. As I shown here, some lines were obtained in emission spectra. So 4 lines were obtained in the emission spectra of the hydrogen atom in the visible range only. So the values are values of the bright lines obtained wavelength. Okay, one obtained lambda 1 in 6583 Armstrong. So it is in the red range, right? Red color. Lambda 2 4861 Armstrong. Lambda 3 4341 Armstrong, and the lambda 4 4102 Armstrong. So first of all, why these lines are obtaining, they did not explain, but they were trying to giving some mathematical justification or physical justification. Physical justification, where there are no physical justification. Anyone cannot give able to give that in physical justification to these results. Even the Rutherford atomic theory also came after 1901, I think at 1903 or 02, at that range, after in 20th century, in early 20th century. But these results were obtained in 1880. So there, in that time, there are no physical justification. But Balmer, he was a mathematician, he gave some mathematical justification of this result. So what was those mathematical justification? He analyzed that if you consider this kind of equation, 1 by lambda equals to a into 1 minus 2 square divided by 1 minus n square. Now if you vary n 3, 4, 5 and so on, that means greater than 2, and if you choose a particular value of a, fixed value, constant value, which was taken by Balmer, was this value, meter inverse, because lambda has the unit of meter inverse and this is just the number, so it should be the unit of a, should have the unit of meter inverse. So then you can obtain the results. Means if you choose n equals to 3, then you obtained lambda equals to, from this lesson you obtain lambda equals to this one, this value. N equals to 4, then lambda will be 4861 Armstrong. If n equals to 5, then lambda will be 4341 Armstrong. Similarly for 6, it will be lambda equals to. So these results were obtained, but he did not able to explain why the a is there, why the value of a should be like this. These explanations were not there because he gave some mathematical explanation. Okay, so this explanation was there. Now if you also have the n equals to 7, 8, but those if you put the n equals to 7 or 8, the value of lambda will not be in the visible range. That's why we are not considering this, but you can put those values as well. So these results were there. So that's why this series, these lines, 4 lines are called as Balmer series. So Balmer's explain this, not explain, give some justification, mathematical justification you can rather say. Now similarly, other parts of the spectrum also be given some kind of similar kind of mathematical justification. Okay, so just like other series, as I discussed in the last class also, let me write it again. For the Lyman series, Lyman also gave some similar justification. Okay, for the ultraviolet region, for the UV region, he also gave similar kind of equation, 1 by lambda equals to a into 1 by 1 square minus 1 by n square. Now you can vary n greater than 1, 2, 3, 4, 5, 6, 7. So there will be lines. So those lines are called the Lyman series. After that there is Paschen series. So he also gave relation, but this lies in IR region. Equation is also same, the value of a is also same, but this is just 3 square. Okay, next, so Lyman, then Balmer, because in Balmer it is 2, then Paschen. After that it's like, but it was first given by the Balmer, that's why it's so much important, and it lies in the visible region, so that's why the Balmer series is most important one. After that, that is the bracket series. Okay, bracket series is also lies in that region, actually IR region we can say. Yes, that is also same, but just it's 1 by 4 square, means 5, 6. We generally don't take the values n greater than 7, because that's the wavelength is much more higher. Okay, okay. After the last one is food, and the intensity of those lines are very less. It's difficult to visible, actually difficult to capture or analyze, so that's why you are not take those lines, because the intensity is very less. So it also lies in the higher region. So basically we are dealing in the UV range to higher range. So here only 2 lines will obtain 617. Okay, so Rydberg, after having these lines, all these lines, Rydberg gives some general expression that is called the Rydberg formula. He just generalized all the result, and he obtained that. We have discussed this in the last class also. This is the general form. Okay, where R is the constant, the same thing as A is there, the same constant we can say, and lambda is same. Now what is M and what M, A, N, B? Okay, A, B are the characteristic constant for a particular series. So A and B are the series constant, we can say, for particular series it will be constant. And what are the M and N? M is a whole number which is constant for a given series. So M is constant for a given series, and N is the same N, the varying part. So N is a whole number which is varying and have the different value, which indicates the different lines in the series. So this is the generalization. So if you want to derive the Balmer series from this Rydberg formula, then what we have to put, R is equal to A. That is not the case, but what will be the A and what will be the B and N? So M is 0, A is 2 constant for Balmer series, N is N, and B is also 0. So if you put M and B 0 and A is 2, then it will reduces to the Balmer series. So similarly you can derive the other series as well, but this is the generalized formula, and Rydberg calculate this value of R more precisely, and the value of R actually obtained that it is actually 1.09678 that I have written in the last pass, because these values, okay, this value of R was calculated by Rydberg. I written the value of A here, but that was not calculated by the Balmer. That was calculated by the Rydberg basically. That's why it's called the Rydberg constant, and it's because it's a constant. So this was the experimental result that time scientists had. They were trying to prove these results, but they were not able. So this atomic spectrum was very much mysterious to them. After that, Rutherford gave some model, but that model was not also able to explain these results. So atomic spectrum was very challenging to explain. So Bohr tries to explain those atomic spectrum basically. He had this result, he knows. So he kind of did some back calculation. He was taking some he wanted to prove this relation, this Rydberg formula by hook and crook. That's why he was taking some ad hoc approximation and start deriving and wanted to reach this particular formula. That was the total scheme of the Bohr. But and one day he succeeded, and that was excellent. What he considered? He considered MVR equals to NH by 2 pi. After considering this, he just did the classical derivation. That derivation is very trivial, you know. We have done, and after doing that derivation, this was the Bohr's quantum postulate, right? By using this postulate, he derived and he obtained the energy values, and now from those energy values you can justify these results, these experimental results of hydrogen spectrum that we'll now see. So we know what was the values. So En should be minus RCH divided by n square. That's why we have considered those value as R actually, because that matches with the experimental value of this Rydberg constant. So that's why this was written as R. So for make differentiation, we can write it in different notation. Let's say this is what we can say xi, or okay, it's xi ch by n square. Let's say it's not the, okay, let it remain as R, but it can be other thing, so that we can make differentiate. So let it be rho. Okay, so that in the part of the analysis we have done for the hydrogen atom, the energy value was this one, RCH by n square, right, general value. And what was the R? Actually the formula was this, m squares CH divided by 8 epsilon naught square CH cube, and CC will not be there. This was the energy value. We ad hocly put CH in denominator and numerator. After that we converted into the wavelength unit, and we said these values are something like this. We did those things to tally with the experimental results. Okay, that is the case basically. So let's say so better to continue with those notations so that we can make direct comparison. Okay, so this was the case, and R is, and the value was obtained, this is okay 1.09737 10 to the power 7 meter inverse. So we can see this value is not same, this is different value. Experimental value is 1.09678. it's some different, so we can say this is theoretical value and that is experimental value. There is a close match, 99% match you can say. Okay, so this actually justified the results. Okay, so this is the Rydberg constant. Now you can easily justify what was the Bohr's postulates? Third, in Bohr's second, this is Bohr's third postulate. In second postulate, Bohr said that in first postulate he first totally nullify the probability of the continuous emission, because he said that in a stable orbit there is no emission, no absorption of energy due to the revolving around the nucleus. So that part is clear. But in second postulate, he said that the absorption or emission of the energy can be occurred due to the transition from one energy level to other energy level. So these are the energy gaps. So general formula of the required energy for this transition should be daily equals to Ni to Nf. The energy gap should be same, the daily should be same. If it is excitation, then it will absorb the energy from source from outside, and if it is de-excitation, then it will emit the energy. This is the case. If it is absorption spectra, then it will absorb the energy from the light, so those photon will be absorbed and those line will be missing in the spectrum, that is the absorption spectrum. And if it is emission spectrum, those excitation will be governed by the electric charges, electric discharges, we can say electric forces. After those transition, the atom will be again stabilized and it will give it will be de-excited from the excited state to the ground state, and same amount of energy will be radiated, and the frequency will be same. So those frequency will be shown in the dark emission spectra as a visible line. So this is the case, this is the emission spectra, but the daily should be the same. So this should be the h nu. The nu is the corresponding frequency. So this is the day, and now if you put it, then we obtain this should be minus RCH Nf square. Okay. Now you know that C equals to nu lambda, and h will be cancelled out from both sides. H is cancelled out. C equal to nu lambda. If you put nu will be cancelled out, and lambda will be this side. So this is the expression. So in general we can write 1 by lambda should be R into 1 by okay. So this is the expression of the lambdas we can have. Now if you vary, you can vary Nf and Nf. Nf is also 1, 2, 3 and so on. Ni is also 1, 2, 3 so on. So we can have infinite number of combination, but all intensities are not same. So now if you put Nf is equal to 1, and if you vary Ni, then you will have the Paschen series. So what is the general expression obtained by Bohr's atomic model? This is just right. So this is the Bohr's atomic model results. Now if you put Nf is equal to 1, and if you varies Ni, then you can obtain that 1 by lambda should equals to R into 1 by 1 square divided by 1 by Ni square. So it is actually the Paschen series. Similarly, if Nf is 2, here actually you are taking the emission spectra, so this is the de-excitation. Okay, here these results is actually for the emission spectra. Okay, that's why how we have identified that, because this is Ni. I means initial energy level. So initial energy level has a higher energy. So that's why daily is positive. We generally take the difference as a positive quantity. So that must signify that Ni is greater than Nf. So that means that the excitation occur from ith level to Ni level to Nf level. That means here the excitation occurs to level 2 and Ni is varying. So then it is the Balmer series. The results we know, the expressions we know. Similarly, other series can also be obtained. So let me write it. For 3, it is okay, not Paschen, it is Lehman. This is Paschen. Nf equals to 4, this is bracket, and Nf equals to 5, CK ETT. it is actually found. Okay, so these are the series. If you want to see in okay, so it is 2. So now when it is coming at 2 means, let's say 3 to 2, 4 to 2, 5 to 2, 6 to 2, 7 to 2. So these are the Balmer series, by Balmer lines of the Balmer series. Okay, the red lines. For 1 it will be from 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1, 7 to 1. So this is the Lehman series. Okay, now for the Passion it will up to 3, so it should be from 4 to 3, 5 to 3, 6 to 3, 7 to 3. This is the Passion series. Next is bracket. Bracket will be at 4. 4 means at 5 to 4, 6 to 4, 7 to 4. This is bracket, and at last it's just the Hund. Hund has should be 6 to 5 and 7 to 5. Okay, so these are the series. Okay, this was totally explained by the Bohr's atomic theory, the results, experimental results. So this was the great achievement of the Bohr's theory. That is why it is well celebrated, we can say. Now if you want to look at the drawbacks, or yes, so we this was the achievement, and totally experimental atomics, the results of the hydrogen spectrum was explained totally by the Bohr atomic hypothesis, Bohr atomic model. So now if you look at the summarize the Bohr's atomic theory: success and failure of Bohr's theory. So okay, so let me stop here in this part. In next part I will discuss this Bohr, the success and the failure, and we'll later discuss the ionization energy and the ionization potential. Then we'll can say that this part, Bohr's atomic spectrum part, Bohr atomic theory part, will be completed, and the next target will be the X-ray part. Okay, so let me stop here in this part. We'll continue from here in the next part.